So you have now completed the first step of numerical calculus, that was the interpolation. Now we will extend this idea to numerical differentiation. In particular, we'll talk about numerical differentiation using a method called finite difference. Numerical differentiation is a very important idea in numerical methods. In particular, this is the gateway of numerical solution of ordinary as well as partial differential equation. So let us see how we can evaluate numerical differentiation using the method of finite difference. Consider a function u which is a function of x and which is differentiable. The function is defined in certain interval a, b. In numerical methods we also use this term very often, that is domain instead of interval. Now we know that analytically the derivative is denoted as u prime or du dx. The magnitude of derivative at x equals x naught is equal to limit delta x tends to 0 delta u divided by delta x at x equals x naught, which we can write at limit delta x tends to 0 u x naught plus delta x minus u of x naught divided by delta x. This is one way of writing. Another way is to write u x naught minus u x naught minus delta x divided by delta x. This is sort of forward and this is sort of backward. In other sense, the way you have learned in your high school, we call this right hand limit, left hand limit. Now this idea of derivative is not like this when we talk in a numerical sense, because the idea of continuity is not applicable here. In numerical method, our domain or this interval a, b is discretized. This is not continuous anymore. Therefore, this idea of limit tends to 0 does not apply there. So if this is your actual domain going from x equals a to x equals b, in numerical methods, the functions are available only at these discrete blue points. In between these blue points, we don't know anything about it. So everything we talk about are there in blue points or at certain discrete points. We have the liberty to define these discrete points. We can take more discrete points. We can make the discrete points denser. But that's about it. We will always have discrete points in numerical method. Unlike in analytical technique where these discrete points does not come into picture, here in numerical method everything is about these discrete points. Okay, so this derivative is available only at these discrete grid points, and at these grid points the value of x, we say that there is xi where I goes from 1 to n. Let us assume that there are this n number of discrete grid points. So we start with an assumption of uniform grid. By uniform grid we mean that xi plus 1 minus xi, that is delta x, that is constant for all grids. So for instance, this is 1 2 3 4 5, this is my x5, this is x6, this is x7. So the distance between x5 and x6 is same as the distance between x6 and x7, is same at the distance between x7 and x8, etc., etc. And also at each grid point I know the value of u. Value of u is defined at those points. So ui is u at x equals xi, ui plus 1 is equal to u at x equals xi plus 1, ui minus 1 is u at x equals xi minus 1. So now we are ready to give some sort of an equivalent definition of derivative, we keep in mind the analytical derivative. The definition of that is limit delta x to 0, this u x naught plus delta x minus u x naught, or u x naught minus u x naught minus delta x, etc., etc. Numerically, we can have this uniform grid here, and let us say we are taking these 3 points just for simplicity, I minus 1, I, and I plus 1, and my delta x is xi plus 1 minus xi. That is, this is my delta x, which is same as this xi minus I minus 1. That means same as this. So the grid size is uniform. Ui is u at x equals xi. Ui plus 1 is u x equals xi plus 1. We can write that this is x equals xi plus delta x. Similarly, I minus 1 is u at x equals xi minus 1. We can write this is u at xi minus delta x. Therefore, taking a cue from the definition of analytical derivative like this, we can write this du dx at x equals xi. This is now numerical, and that should be del u del x at x equals xi. And here we are not using this limit anymore. This is ui plus 1 minus ui by delta x, which is equivalent to this x naught plus delta x. I plus 1 means xi plus delta x. So this is xi plus delta x minus xi. So ui plus 1 minus ui divided by delta x. We assume that, well, my delta x is small enough, so this is my limit. I cannot go any less than delta x because we are in discretized domain. This is one of my x, then next x is here, so I cannot jump in between. So this is something we call forward difference. Similarly, we can have backward difference, ui minus I minus 1 this side, and also we can have central difference, taking I plus 1 and I minus 1 divided by the difference between these two, that is twice of delta x. So these three ways we can define the derivative, and we will confine our discussion to this for some time. All these definitions are actually right, and all of them are approximate. If you calculate that for any known function, you will find that they may not match with the analytical solution, and they may not match with each other, and yet all of them are, in numerical sense, they are right. Although each of them contains certain error, and all those errors may not be same. The errors are the difference between numerical and analytical derivative. This is the method of differentiation which we call finite difference method. Let us now take a function. Let us say that this is u equals 2x square plus x plus 1. If I take a derivative, it will give me 4x plus 1. If I take the value of derivative at x equals 0, that will be simply 1. Now let's see that if we calculate this derivative numerically using all three methods, forward, backward, and central, what do you get? So this is my uniform grid. My grid size is 0.1. So I have from x equal to 0, 0.1 forward and 0.1 backward, and my u is only defined at these 3 points. Since u is 2x square plus x plus 1, I can get the value of u at these 3 points. For example, u negative 0.1 is 0.92, u 0 means this is 0, that is 1, u 0.1 means 1.1, 2 into 0.01, that means 1.12, etc. Now that I have these 3 points, it's easy to get the derivative. Forward difference is coming from here to here. That means here at 0.1, this is 1.12. So this is 1.12 minus 1. 1.12 minus 1 divided by delta x, that is 0.1. So that gives me 1.2. We can see that my analytical is 1. I am getting 1.2 here. Backward difference will be x equal to 0, that is 1, minus x equal to minus 0.1, that is 0.92. So 1 minus 0.92 divided by 0.1, that should be 0.8. And finally, central difference. Central difference, you will see that 1.12 minus 0.92 divided by 0.2 will give you 1, which in this case is matching with the exact solution. Why it is matching and why others are not matching? These are the questions we will see in upcoming lecture. And will it match for all functions or will it not? That also you can try and see. So we have now learned at least to differentiate functions numerically. For your exercise, you do a very similar problem that we have just solved. Here you take u equals 2x cubed plus x plus 1. First you find the derivative analytically from first principle, means evaluate the limit and find the derivative. Then calculate the numerical derivative at x equals 0 with a grid size of 0.1 using forward, backward and central difference. Finally, you check the error. Error means the absolute difference between analytical and numerical solution. That's all for this lecture. Thank you, and I'll see you in next class.